Assalamualaikum and a very good day, Abid, to the fellow panels and lecturers. I'm Aina Sofia binti Muhammad Zulkifli. Today I'll be presenting to you my research proposal with the title of Blood Flow Mechanism of Riblet-Enhanced Hemodynamics on Artificial Heart Valve for Reducing Thrombosis Risk. So for this project, I'll be supervised by Dr. Muhammad Shukri bin Zakaria alongside my co-supervisor, Prof. Madya Dr. Muhammad Juzaila Abdul Latif. Right. Mechanical heart valve have been widely used for over 70 years due to their long lifespan and mechanical durability. However, one of the major issue with a mechanical heart valve is thrombosis or blood clot formation, which can lead to a life-threatening complication. Because of this, patients often require a lifelong anticoagulation intake. By understanding the blood flow behavior or hemodynamics is therefore crucial to reduce the thrombosis risk. So this study proposed a Riblet-enhanced heart valve design using computational fluid dynamics to study how small surface growths can influence blood flow and minimize clot formation. So this study will be conducted in 3 phases. The first phase will be focusing on numerical modeling of the riblet flow. Phase 2 on optimizing the riblet geometry, and phase 3 is on evaluating the optimized design in a patient-specific aorta. All right, for problem statement, mechanical heart valves are designed to maintain unidirectional blood flow, or meaning that blood only flow in one direction. But blood clot formation can impair valve function, which preventing the valve to open and close fully. And the worst case scenario, it can cause a severe complication, such as stroke. So you can see in the figure below where the blood clot accumulation that impair the valve function. Okay, high wall shear stress caused by flow friction on valve surfaces is strongly linked to the thrombosis. Recent research by Wong et al., although vertex generator have been used to reduce turbulence, yet their geometry creates additional drag. And Abasi and Katabdari stated that riblet microstructure that inspired by the shark skin has a promising in improving flow and lowering thrombosis risk. However, the modeling remains challenging due to their microscopic size and complex flow behavior. Hence, this study aims to explore riblet-enhanced flow mechanism to reduce wall shear stress and minimize thrombosis risk in mechanical heart valve. So this study have 3 research objectives. The first one is to elucidate the efficacy of riblets using canonical flow channel and flow over a flat plate through a turbulent Raynaud shear stress reduction between smooth and riblet surfaces. Number 2 is to investigate the effect of groove geometry, shape and size on fluid flow and thrombosis index in a simplified model of a mechanical heart valve. And the last one is to analyze the wall shear stress on the patient-specific aorta ascending wall and a artery outlet implanted with a mechanical heart valve integrated with groove riblets. So the main hypothesis of this research is that incorporating riblet structures on valve leaflet will reduce wall shear stress and promote laminar blood flow, thereby decreasing thrombosis risk. To support this hypothesis, the study will answer 3 key questions. The first one is how does the geometry of riblet affect the flow and shear stress? Number 2, how do flow conditions such as Reynolds number and flow rate influence the riblet performance? And number 3, can riblet integration actually reduce thrombosis and hemolysis in a patient-specific aorta? Right, now moving on to the literature overview. So several previous studies have highlighted the link between blood flow dynamics and thrombosis. For example, from his predictive model, Hotum has found out that abnormal blood flow can actually lead to thrombosis and hemolysis. Other than that, Zakaria et al. Showed that Computational fluid dynamic simulation can effectively analyze flow patterns and shear stresses in artificial heart valve. Based on the most recent study made by Wong et al., um, the vertex generators has proven reducing the turbulence. However, the profile itself still causes a high drag. On the other hand, Zhang et al. Has found out that the riblet surface composed of small streamwise ridges inspired by shark skin is one of the promising passive drag reduction technique in boundary layer. Also, he stated that riblets has been proven to reduce drag by 4 to 7% in aerospace and marine industry application. So various structures such as blade, scallop, and sawtooth have been extensively studied in turbine blades and through numerical simulation. So in my project, I'll be using the scallop as U groove, while sawtooth is a V groove patterns. Okay. Um, However, no existing study has examined the riblet-covered valve leaflet and their influence in wall shear stresses. So this research aims to fill that gap by analyzing the detailed mechanism of blood flow through a riblet surfaces. Right, moving on to the research methodology. So for phase one, focusing on the direct numerical simulation of the riblet flow. So the riblet will be modeled as small periodic grooves on a flat plate, and the simulation will be performed using ANSYS Fluent and validated against two benchmark cases. So the first case is the flow over an obstacle, and the second one is a flow over a flat plate. For the numerical analysis, equation 1 is the mass conservation, and equation 2 is momentum conservation Navier-Stokes that will govern the fluid flow motion and will be solved accordingly. Equation 3 is the wall shear stress calculated as the shear rate normal to a wall times the viscosity of the flowing fluid. So this concept brings a wall shear stress as the frictional force that flowing fluid tangentially influence a wall, both magnitude and direction. So the next is the Reynolds shear stress will be computed in equation 4. So the Reynolds shear stress has been widely correlated to turbulence and platelet activation. It is a statistical quantity that measures the shear stress between fluid layer when fluid particles accelerate or decelerate while changing direction. And last but not least, the efficacy calculation comparing the smooth leaflet and riveted leaflet in equation 5. So in phase 2, the riblet will be applied to the surface of a mechanical heart valve leaflet. 15 different riblet configuration will be tested, which is 3 shapes with 5 different sizes each. We have blade, U-groove, and V-groove structure. Also, the riblet will be designed parallel to blood flow. CFD simulation will help identify which geometry provides the most effective reduction in shear stress while maintaining smooth flow. So the outcome of this phase is to select the optimized riblet shape and size for further analysis. Right, phase 3 involves testing the optimized riblet design on a patient-specific aorta model. So the model will be simulated under physiological condition to compare two cases. The first one is a smooth valve surface and second one riblet covered surface. So the analysis will focus on flow velocity, pressure distribution, wall shear stress, and region prone to thrombosis, such as thoracic aorta, brachiocephalic artery, left common carotid artery, and left subclavian artery. So this phase will determine how effective the riblet design is in real human geometry. So as you can see in a figure here, this is a CT scan data obtained from a 59 years old patient. As for the expected outcomes, first, reduce wall shear stress and Raynaud shear stress, leading to smoother, more laminar blood flow and reduced thrombosis risk. Second, identification of an optimized riblet geometry that balance drag reduction and stable flow. Third, a validated CFD and 3D printed model that can be used for future experimental studies. So overall, this project aims to contribute to the development of next generation heart valve that can resist the thrombosis risk. Right, this project is planned over a 24-month period. The first 6 months will focus on the phase one, and by month 12, we'll start with phase two, and following with phase three on the month 18. And finally, by month 24, the thrombosis risk evaluation and full analysis will be completed. So this structured timeline ensures progressive validation at each stage. Okay, here is the Gantt chart to keep this project on track and successfully achieve the objective. In conclusion, this research aims to provide a new approach to reduce thrombosis in mechanical heart valve through Riblet-Enhanced surface design. By integrating computational modeling and bio-inspired engineering, the study will deepen our understanding of how surface microstructure can influence hemodynamics. Ultimately, the findings could contribute to safer, more efficient, and long-lasting artificial heart valve. So here is the references I've used for this research proposal. Like same goes to this page. And I guess that's all for my presentation today. Thank you very much for your attention. Thank you very much for your time and wish you have a good day ahead. Thank you.